So, hello everyone. Gitanjali Jaina. I'm a PhD scholar from IIT Delhi. So, I'm also a PMRFT for this course, which is Introduction to Laser, taught by Professor M.R. Sinha from IIT Delhi. So, in each live section, as I said, we'll go through the weekly concept and as well as the weekly assignment. And whatever doubts regarding the assignment or any concept that you must have, I will try to clarify during the live section. And besides that, I will try to solve a few additional problems that is different from the assignment to help you to understand the concept better as well as for the numerical purpose also. So before starting the session, uh, let me ask whether you have any doubts in week 11 assignment. The solution has been released in the portal for week 11. So if you have any doubt in the solution or you have got any different answer or anything related to week 11 assignment, please ask me now so that I can first clarify your doubts first, then we'll go through the remaining concept that is related to the previous session as well as the current session. So please feel free to ask me the doubts. Uh, you can unmute yourself to ask the doubt, or you can also write it in the chat box if you are not able to unmute yourself. So I have unmuted everyone. So uh, let me see whether you have any doubt. Uh, okay. So one question is about the exam week, not to miss in preparation. So exam week, I have already talked with the NPTEL team. I have asked them to uh, provide the tentative schedules in the discussion forum or in the announcement. So they are working on it. So you will soon get the what is the tentative dates of exam and week and all. And regarding preparation, I would suggest please go through the lecture slides and the weekly assignment as well as a few additional problem that I'm covering in the during the live session. So this all is enough for you to prepare for the exam. So nothing additional is required. Only conceptual as I said in one of the live section, the problems are mostly one is assignment based. So that question will be not exactly similar to assignment, but it is kind of similar to assignment. Means there is some numerical change and all. So one is assignment based, so you have to go through the assignment again so that you will be confident to solve any problem. And for concept and other type of question that will be asked is conceptual one. So you have to go through the lecture slides again so that you can clarify your concept. And other one is numerical based, like in the assignment you have been asked to you have been given some parameters to find out this value, so that this type of question will be also be asked in the final exam. So please go through the assignment problems and the lecture slides and few problems that I solved during the live section. These are enough for you to appear in the exam. Okay. Any additional thing is not required for this course because it's the introductory course. So, mm, dif- uh, so question will be mostly conceptual and assignment based and numerical. So I think this clarify your doubts, Ananya. So let me know if you have any further doubt. Okay. So one query is question 4 of week 11. Question 4 of, so let me see the question first. Mm, Question 4. So give me a few minutes more. This is okay. So, okay. So this is the question says which one of the following is not an advantage in using a exfold cavity for diode pumped solid-state laser ND Yttrium VO4 laser. So multiple output beams of different wavelength can be obtained by switchable array effect. So first one is obviously one advantage of using exfold cavity. The pump power conversion efficiency is enhanced as compared to a typical two mirror cavity laser. Okay. The exfold cavity facilitates the insertion of additional optical component in the resonator. Yes, this is also possible. The exfold cavity enables unidirectional propagation of the laser beam inside the cavity. Uh, mm, yes, this is also possible using isolator. Second is the pump power conversion efficiency is enhanced as compared to a typical two mirror cavity laser. Okay. So, Nitish, can you please tell me your doubt specifically? Like other three options are obvious because other three are not possible in a typical two mirror cavity. So if you use X-fold cavity, then we'll be able to insert additional
Ma'am,
optical component.
ma'am, fourth
Okay.
is the property of X-fold.
It's not a property of X-fold, but it's like if you insert a isolator inside the X-fold cavity, because X-fold cavity it enables optical integration. So because of that, you can integrate isolator in the X-fold cavity to enable the unidirectional propagation.
Yeah,
It's like unidirectional is not possible in other type of a laser, but if you use X-fold cavity, then we can integrate more optical component in the cavity. So that's why it's a advantage.
okay, okay. Thank you, ma'am.
Okay. Any other doubt? Anyone? I think other questions are obvious to answer. Okay. So if not, let us move to our uh, remaining concept that we have not covered in the last live section. So I will try to cover the week 11 concept quickly so that we can move on to the week 12 concept. Okay. Besides, we will solve a few problems that is related to week 11 uh, in the meantime. Okay. So In the last live section, we were covering what are the different type of heterostructure and what are homojunction, what are heterojunction, and what will happen when you use homojunction and heterojunction. So, what are the typical characteristics of using homo and heterojunction? So, previously we have seen in homojunction there is only one Fermi level, and at equilibrium the total current is zero. That is, the diffusion current is neutralized by the drift current. But when you apply any external biasing, like if you connect a battery to the PN junction diode, or you can or you supply any power supply, then it's a biased condition. So when you forward bias the PN junction, what will happen? So it will give potential to the carriers like electrons and holes to move to the depletion region. So earlier there was a depletion region because of some immobile ions in the depletion region. So, but when you forward bias it using a battery, we will see the carriers, the electrons and the holes will move to the depletion region, which is shown in this diagram. Okay, and instead of one Fermi level, we will have two Fermi level. One is Fermi levels, quasi Fermi levels for the conduction band, and quasi Fermi levels for the valence band for the p dot. And let us see what are the changes in the carrier concentration when we move from thermal equilibrium to a quasi equilibrium. So in thermal equilibrium, we have one Fermi level, and the carrier distribution is given by this equation, which is n equal to nc e to power ef minus ec by kBt. So ef is the Fermi level of the band, and ec is the condension band age. And similarly for P concentration, that is hole concentration, we have P equal to NV e to power EV minus EF by kBt. And if you multiply it both N and P, what we have NP equal to NCNV e to power EV minus EC divided by kBt, which is this equation. Okay. So So now, if you compare it, if you put the value of EV minus EC, which is equal to EZ, EZ is the band gap energy, right? So what you have NP equal to NC NV e to power minus EZ by kVt, which is equal to Ni square. And this NP equal to Ni square, which is N here is the electron concentration, P is the hole concentration, Ni is the intrinsic carrier concentration. So this is known as law of mass action. So this law of mass action is valid only at thermal equilibrium. It's not valid when you bias the system. Okay. So now let us see what is the changes that has been done when you bias the system using any external battery or external voltage. So for quasi-equilibrium, we have seen we have two Fermi levels. One is EFC and other one is EFV. Okay, and the carrier concentration in n-doped, it is given by n equal to nc e to power EFC minus EC by kBt. So if the Fermi level, which is the common Fermi level in thermal equilibrium, it will be replaced by EFC for quasi-equilibrium. And similarly, whatever equation that we have in the thermal equilibrium condition, that is, this is P, the distribution for the whole concentration. So only the EV, it will be replaced by, EF, it is replaced by EFV because EF is now different. And if you multiply it, what is the equation you will get? So you get NP equal to Ni square, which is law of mass action, multiplied by a factor, which is e to power EFC minus EFB by kVt. So you can see at thermal equilibrium, we have NP equal to Ni square, but when we move from equilibrium to a bi state, we have Np equal to Ni square with a factor, which is this exponential factor. So as I said, law of mass action is not valid in thermal equilibrium. So we always have Np is greater than Ni square for quasi-equilibrium condition case. So if you're given this type of semiconductor, what is the condition required for laser action? So if you recall, for laser to lace, the population inversion condition should be valid. That is, delta n should be greater than 0. That is n2 minus n1 greater than 0. Of if you write more specifically, it should be sigma 2 n2 minus sigma n n1. It should be greater than 0. And when sigma 2 is equal to sigma 1, then we can tell delta n should be greater than 0. Similarly, in semiconductor, what is the equivalent condition? This is the equivalent condition for lasing to happen in a semiconductor. So EFC minus EFV, which is the separation between the Fermi levels of conduction band and the valence band, it should be greater than the band gap energy. Okay. So only in that condition, the semiconductor will behave like a laser and it will emit radiation in terms of stimulated emission. So please remember this condition. This is a one important relation for lasing in a semiconductor. So let us see how the carriers are confined inside a heterojunction. Heterostructure is a semiconductor. So if you recall, a heterostructure are nothing but two different type of semiconductor are these are sandwiched between a active layer. So if you see this figure, so this is the band structure for a heterostructure semiconductor. One is in one side where this is p dot, in other side it is n dot. And in between this two semiconductor, there is a small region which is band gap energy smaller than this p and n dot semiconductor. Okay, and when you combine all of this, what will happen? So at equilibrium, the electrons will move from N to P side and the holes will move from P to N side. And after some time, what will happen? There will be a depletion region where immobile ions are localized in this region, which prevents the further movement of electrons from N side to P side or holes from P side to N side. So because of that, we'll see there is a depletion region forming in this active layer. But when you forward bias it, what will happen? So this will help the electrons from the N side to move to the active region and for the hole to move from P to the active region. So you can see in between this in this active region, in this small active region, which is thickness around zero 0.1 micrometer, these electrons and holes are tightly confined. So you can see how you can see how the carriers are confined in this small region. That means the heterojunction, it improves the carrier confinement when you forward bias it. So this is carrier confinement in the active layer. And the other thing is, other advantages of using heterostructure is the optical confinement. So by optical confinement, so this you have to remember that this is the relation between how the refractive index is qualitatively related to the band gap energy. So EZ, which is the band gap energy, it is inversely proportional to, I think this is not visible. So EZ, it is inversely proportional to the refractive index. Okay. So So that means the materials which is lower band gap energy that will have higher refractive index, and the materials which is higher band gap energy that will have lower refractive index. So now if you relate this relation to the heterostructure, so in heterostructure you can if you see this diagram, you can see the Eg2. So Eg2 is less than Eg1. So that means refractive index of this active layer, it is greater than the refractive index of the surrounding semiconductor. So that means when you combine this different type of semiconductor, when you sandwich them, like the n-doped algas with gallium arsenide, and the n-doped algas with gallium. So there is, so for junction, it should be p type, not n type. So this one, I think this has been used for understanding purpose. But when you make a junction, on one side it is p and on other side it is n. So if you see, when you combine them, you can see you can plot a refractive index profile for this type of sandwiching. So for n-doped, the refractive index would be, let's say, 3.4, and for active layer it is 3.6, and on other side it is p-doped and it is 3.4. So we can see the refractive index is high in the active region, and in the surrounding region the refractive index is low. And this profile is similar to a the condition that is required for total internal reflection. So if you recall, for total internal reflection to happen, the refractive index of uh, the middle region should be greater than the refractive index of the surrounding region. So that means if you launch a light into this heterojunction semiconductor, then the light will be total. It will be reflected totally inside this N2 layer. Okay, so it will not be absorbed by the surrounding layer. It will be confined inside this active layer. So this is what we mean by optical confinement, which is done by sandwiching different type of semiconductor through a junction. Okay, and the standard laser diode, it behaves like a Fabry Perot laser, where when you launch the light get reflected back and forth between the p-type algas and n-type algas, and it behaves like a laser by emitting radiation in terms of stimulated emission. And as we have seen, the laser consists of a resonator and a gain medium. Okay, and let us see what we have now. So these two scientists, Alferev and Kromer, they have been awarded Nobel Prize in 2000 for developing semiconductor heterostructure used in high-speed devices and optoelectronics, and for basic work on information and communication technology. So this indicates how this development of heterostructure has been crucial for developing semiconductor laser and for optical communication. So there are two types of Fabry-Perot laser. One is the gain-guided laser, and another one is the index-guided laser. Okay. So and to fabricate these, so we have these techniques: MBE, BPE, and MOCVD. So in gain-guided laser, what we have, the due to the movement of this carrier, there will be a gain in the system in the region where the carriers are flowing. Okay. So because of this carrier movement, we'll see gain in the system. But in index guided mode, what we have, the refractive, because of the change in refractive index, so we have the, if you see this case, the refractive index is low in this region, but it is high in this region. So because of this, we'll see guidance in both transverse direction due to the refractive index profile. And what will happen? What is the typical response of a laser when you when you operate it below threshold? So below threshold, what we have, we see only spontaneous emission. So when you inject current to this PN junction diode, so what will happen? The spontaneous emission will happen, and because of that, we'll see the spectrum will look like this. And depending on the change of when you increase the injection current, the spontaneous emission will increase gradually. And now when the laser, so when you supply a current which is above the threshold, that is the threshold required for stimulated emission, what will happen? So you will see the oscillation of longitudinal modes inside the cavity because of the current which is value which is above 10, the threshold value. So these are the longitudinal modes that will oscillate when we inject current which is greater than the threshold value. So because of that, what you will see that suddenly when you operate the system above the threshold, the current will peak. So we'll see the current value will increase suddenly when you work it on when you operate it on above threshold value. So let us see how we can make a single frequency laser. So previously we have discussed for single frequency oscillation what is the component we have used. So we have used intracavity tilted Fabry-Perot Itala. So the principle is it is shown in this figure. So these are the longitudinal modes of the cavity, and this is the gain curve. And for laser to oscillate, the gain should be greater than the loss. So for single frequency oscillation, what we need that the losses in other longitudinal oscillation should be higher than the losses in the frequency where we want to oscillate. So let us say we want to oscillate around this frequency. So we need the loss curve like this. So we need that the losses in at this frequency uh, should be lower than the gain, so that the amplification can happen whenever we uh, oscillate the whenever we operate the system. So these are the concept that we have earlier seen for single frequency oscillation. So for a laser in a semiconductor system, what we need, so what we can use, so we can use grating to for the single frequency oscillation. So one typical example is distributed feedback laser. So if you see in a normal Fabry-Perot laser, so we have p-type semiconductor on one side and sandwiched to a active layer, and n-type semiconductor to a other side. And for this type, we'll see longitudinal oscillation, which is similar to this curve. Okay. And for single frequency oscillation, what has been made? So we can introduce a periodic grating. Okay. So we can introduce a periodic grating in the p-type one of the layer, so that you can make the desired wavelength reflected inside this periodic grating. So if you recall the Bragg condition, so whenever this condition is satisfied, so let us recall, whenever you have a periodic grating like this, and when you launch a wavelength of source of wavelength lambda, and let us say this periodic grating has periodicity gamma. So let us say this symbol is gamma. So whenever this lambda 0, it's satisfied to an effective gamma. So what will happen? The incident light will be reflected back. Okay. And using this concept, the distributed feedback laser is developed. So if you see, there are layers. That one is so this is the active layer where light is generated inside this active layer. This is P, gallium arsenide, and there is a p-type gallium arsenide with different concentration of gallium and aluminum on one side, and there is a n-doped gallium arsenide with different concentration of gallium and aluminum. And if you see the p-type gallium arsenide, then this layer has periodic grating inside it. So what will happen? So let us say this lambda 0, it is satisfying this to an effective gamma. So if this is condition is satisfying, then at every region the light will be reflected back. And because of this anti-reflection coating, so this reflected light will be trapped inside this active layer. It will not be able to pass this anti-reflection coating. But other wavelength, that is other than this lambda 0, let us say lambda I. So this lambda is, these are not satisfying this condition which is required for reflection. So this wavelength will easily pass through this anti-reflection coating, but this lambda 0, which is satisfying this reflection condition, will be trapped inside this active layer. So because of this, we can see there is a oscillation of single frequency inside this active layer. Okay. So let us see what will be the spectrum. So for a typical conventional Fabry-Perot laser, so we have more number of frequency that is oscillating inside this active layer. Also, these are multi-longitudinal mode oscillation. But when you introduce a uh, Bragg grating, periodic Bragg grating inside this layer, the p-doped gallium arsenide, so you can see only a single frequency will be able to oscillate inside the active layer. And this single frequency satisfy this condition, which is lambda 0 equal to 2n effective gamma. So n effective, this is the effective refractive index of the oscillating mode, and gamma, it is the periodicity of this grating, and lambda 0 is the oscillating frequency. Okay, so uh, this is the one of the experimental graph where for a Fabry-Perot cavity, where you see there are multiple frequency that is oscillating inside this active layer, and this is a spectrum width of around 4 nanometer. And when you use this DFV, which is distributed Bragg laser, then you can see only one frequency is able to oscillate inside the laser cavity, inside this active layer, and it has a spectral width of 0.0275 nanometer. Okay, so this is the end of week 11. So these are the typical examples of the DFV laser. One is 1 milliwatt 1550 DFV laser, which is a butterfly package. So this is used for telecom application, and this is operated. This is output power of 1 milliwatt. And other type of this semiconductor laser is 14 pin DIL package, which is high reliability for RWD laser chip. And this typically operate around 1300 nanometer wavelength and give you output power of 2.5 milliwatt. Okay. And these are some of the figures of semiconductor laser of the laboratory. Okay, so this makes the end of week 11. So let me ask whether you have any doubt in the week 11. Otherwise, we'll move to the few problems that is related to this concept. Then we'll see what is there in the week 12. Okay, so let us move to the problems and solution part. So the first question is, what is the purpose of using a dichoic mirror in a diode pumped NdArc laser? So this is easy. I think most of you will be able to answer this question. So let us see the options. So option A is this color is very light. Okay. Mm, so let me then. It's not possible to write the question. So is it too late for you to read the question, or you are able to read the question? So I will change the color once I upload this in the
Visual
Google
में.
Drive. Okay. So if it is not visible to anyone, then let me read out the question. But I will make sure I will write it in other color and upload it in the Google Drive.
Ma'am,
So the
visual.
first, okay. So the first question is, what is the purpose of using a dichoic mirror in a diode pumped NdArc laser? So option A says, what is the, option A is to reduce the loss due to spherical aberration of mirror. Option B is to reflect only the pump wavelength while absorbing all other wavelength. Option C, to provide high reflectivity at the lasing wavelength while transmitting the pump wavelength. And option D is to provide high reflectivity at the pump wavelength while transmitting the laser wavelength. So mm, make sure to read out the option very carefully because there are two options which look similar. But so you have to remember that dichroic mirror are used to transmit the pump wavelength efficiently and to reflect the lasing wavelength efficiently. Okay, so the answer will be option C, which is to provide high reflectivity at the lasing wavelength and transmitting the pump wavelength. So let us move to our next question. So second question is, which type of laser relies on double heterostructure? Option A, helium neon laser. Option B, ruby laser. Option C, diode laser. Option D, NdArc laser. So if you see, the answer will be option C, diode laser. Okay. So let us move to our next problem. So the next problem is based on quantum defect. So the question says, based on the quantum defect, which one of the following laser system is most efficient? So let me tell you the details about quantum defect. So if you recall quantum defect, so this says how much energy of the incident pump wavelength is lost in heat. Okay, so quantum defect or QD, so it quantifies the heat generation in an fiber, and it typically tells you what is the fraction of pump power is lost in form of heat. And what is the formula for quantum defect? So if you recall, it is 1 minus lambda p by lambda L. Okay, so lambda p is the pump wavelength. And lambda L is the laser wavelength. And what do we mean by efficiency? So by efficiency, we mean that most of the energy of the pump, it is converted to the lasing wavelength. So for a system to be more efficient, the heat release should be low. So that means what we want for more efficient system, the quantum defect, that is QD, should be low, so that the heat released is also low. That means the pump power that is converted to the laser wavelength, it is high. So let us see what are the options given. So first option is erbium doped fiber laser, pumped at 1480 nanometer and lasing at 1565 nanometer. So this is nothing but lambda p, and lasing wavelength is lambda L. So option A, it is given lambda p is 1480 nanometer and lambda L is 1565 nanometer. So that means QD, it is 1 minus lambda p by lambda L is 1 minus 1480 divided by 1565, which will come around, think, to calculate. So 1565 by, so it will come around 0.054. The QD will come around like this. So second option, what is saying? ND doped fiber laser pumped at 804 nanometer and lasing at 1064 nanometer. So that means this is lambda p 804 and this is lambda L 1064. So let us calculate. So lambda p is 804 and lambda L is 1064 nanometer. So QD will come around 1 minus 804 divided by 1064, which will come around 0.244. So let us quickly see what is the lambda p and lambda L for the third option. Third option is YV doped fiber laser pumped at 975 nanometer and lasing at 1070 nanometer. So that means lambda p is 975 nanometer and lambda L is 1070 nanometer, which will give QD equal to 1 minus 975 divided by 1070, which will come around 0.088. And the last option is erbium doped fiber laser pumping at 980 nanometer and lasing at 1550 nanometer. So this is lambda L and this one is lambda P. So lambda P is 980 nanometer and lambda L is 1550 nanometer. So that means QD will come around 1 minus 980 divided by 1550, which will come around 0.3677. So So lowest QD among these is this is 0.054, 0.244, 0.088 and 0.3677. So that means the first option, which is QD 0.054, it is the lowest QD value. That means this system is more efficient for lasing. I think this problem is clear to you. So the answer will be option A. Okay. So if in between you have any doubt in any of the steps, so please feel free to stop me at that time. So I will clarify the doubt at that moment. Okay. So let us see the fourth question. Which one of the following statement regarding diode pumped solid state NdArc laser is incorrect? Option A, using an X-fold cavity enables the placement of additional optical components along the beam path for different application, which is correct. So when you integrate X-fold cavity, so we can integrate additional component along the beam path for different application. So second option, a nonlinear crystal can be used in the cavity to convert the lasing wavelength of 532 nanometer to 1064 nanometer through single harmonic generation. So if you see, this option is incorrect, right? So it says using nonlinear crystal and single harmonic generation, we can convert 532 nanometer to 1064 nanometer. But if you recall nanometer. So if you recall the single harmonic generation, so nonlinear crystal, so when you incident a wave light of frequency omega, so you get the response around 2 omega as well as some part of omega. So in terms of wavelength, it is lambda, and this is lambda by 2, right? So lambda will be down converted to lambda by 2, but the omega, the frequency will be up converted to 2 omega. So the question is saying it is up converting from 530 to 1064 nanometer, which is not correct. So answer is already in option B. So let us see what are the options C and D also. So option C says an optical isolator is used to allow the propagation of light in only one direction, which is correct. And option D is NdArc laser can be pumped by a diode laser at 804 nanometer, which is also correct. So the answer for this question is option B, which is nonlinear crystal can be used in the cavity to convert the lasing wavelength of 532 nanometer to 1064 through single harmonic generation. So let us quickly see what is the next problem. So it is based on the erbium doped fiber laser. So an question says an erbium doped fiber laser is to be designed at a lasing wavelength of 1560 nanometer. Given that the effective refractive index of the guided mode in the fiber at 1560 nanometer wavelength is 1.458, and the period of the fiber bracketing to be used as feedback mirror is days micrometer. So it is saying you want to oscillate so you want to design a single frequency laser, and you are given what is the wavelength you want to oscillate, which is lambda 0 is 1560 nanometer, and effective refractive index is also given. It is 1.458, and it is asking about what is the value gamma, so that it can act as a feedback mechanism. So if you recall, the relation is lambda 0 equal to 2n effective gamma. So that means gamma is lambda 0 divided by 2n effective. So this is easy to solve. 1560, 2 into 1.458, which will come around, I think it will come around 0.5349 micrometer. And the question is saying write your answer up to 3 decimal places. So you have to round it off to 0.535 micrometer. So answer is 0.535 micrometer. So let us move to the next problem. So question 6 says, which one of the following is not a feature of double heterostructure in a semiconductor laser as compared to that of a homojunction device? So which is not a feature of double heterostructure laser? One is strong carrier confinement in the active region, which is we have already seen carrier confinement in the active layer. Second is lower optical confinement, which is not correct. It's a feature of double heterostructure. We can see higher optical confinement, better optical confinement for a double heterostructure laser. So the answer is obviously option B. And other option C is lower absorption losses at the laser wavelength, which is also possible because optical confinement, it decreases the losses, and relatively lower threshold current, which is also correct. So the feature, so the option which is not a feature of double heterostructure is option B, which is lower optical confinement. Okay. So let us see what is the next problem. So question 7 is, which one of the following feature is an advantage of semiconductor lasers over fiber lasers? Option A, Q-switched operation with variable frequency input. Option B, higher power output. Option C, high quality output beam of circular cross section. Option D, feasibility of direct modulation at high speed. So if you look at the option, what is the advantage of using a semiconductor laser? So advantage is feasibility of direct modulation at high speed. So by changing the injection current, you can modulate you can directly modulate at high speed. So the answer will be option D. So when you are going through a option or going through a question, please read all of the options. So it may happen few answer may you may think that the option A is correct and you just write the answer. But please go through the all the options so that you can be sure that yes, this option is correct option. So let us move to the next problem. It's a numerical one. So let me read out the question. In a semiconductor sample at 300 Kelvin, the electron concentration is 2 into 10 to the 13 per centimeter cube. So it is given electron concentration, which is N equal to 2 into 10 to the 13 centimeter cube. If the semiconductor is pumped such that the separation between the quasi-Fermi level is 0.1 electron volt, So when you bias a system, that is when you, so biasing, it's not like you just connect a battery or you just put a voltage on it. So when you use external light, just as you pump a system, then that is also a kind of forward biasing. Okay. So this means that when, so the question, as the question says, if the semiconductor is pumped such that the separation between quasi-Fermi level is 0.1 electron volt, that means EFC minus EFV. So when you pump a system, it is in quasi-equilibrium condition and you get two Fermi levels. And the separation, it is given 0.1 electron volt. Then it is asking calculate the whole concentration in the sample at this temperature. And it is also given the intrinsic carrier concentration, that is Ni, it is 2.5 into 10 to the 13 centimeter cube. So that means Ni is given 2.5 into 10 to the 13 centimeter cube. So this is a direct equation based problem. So Np equal to Ni square with a factor e to power EFC minus EFV divided by KBT. And you need KBT, and if you recall KBT at 300 Kelvin, it is 25 millielectron volt. That is 0.025 electron volt. So now you have all the parameters to calculate what is the whole concentration. So P equal to Ni square by N e to power EFC minus AFV by KBT. So Ni square, it is 2.5 square into 10 to the 26 into e to power EFC minus EFV, it is 0.1 divided by KBT, it is 0.025 whole divided by N. N is 2 into 10 to the 13. And if you calculate it, it will come around 170.62 into 10 to the 13 per centimeter cube. So this is the answer. So that means the whole concentration P is 170.62 into 10 to the 13 per centimeter cube. Okay. So let us move to the next problem. So question 9 is, which one of the following is a correct statement for diode pumped solid state in the YVO4 laser with an X-fold cavity? Which one is the correct statement for this laser with an X-fold cavity? So option 1 says the DPSS in the YVO4 laser cannot be operated without using the X-fold cavity configuration, which is not correct. It can be operated without the X-fold cavity. Option B, X-fold cavity facilitates light to travel in both forward and backward direction, resulting in enhanced output power. Which is not correct, because if you use an isolator, it allows currents, it allows the light to pass through only in one direction. Option C, the X-fold cavity effectively increases the free spectral range of the laser output, which is also not correct. And let us see option D, multiple output beams of different wavelengths can be obtained at different output ports by switchable arrangement in the X-fold cavity, which is correct, right? So this is similar to one of the problem in the assignment, I think. So answer will be option D. So let us move to our next problem. So next problem is, which one of the following frequency selective filter arrangement is most suitable for use in a tunable frequency laser? Option A, external cavity reflection grating. Option B, prism mirror combination. Option C, acousto-optic tunable filter. Option D, electro-optic tunable filter. So which one is most suitable for tunable frequency laser? So if you take external cavity laser reflection gating, then it is more suitable for use in a tunable frequency laser. So answer will be option A, external cavity reflection grating. So we have solved 10 problems that is related to week 11. So I think this all these problems are clear to you. So I have solved numericals as well as conceptual. So let me know whether you have you have any doubt in any of this question. Otherwise, we'll move to week 12. So if no any doubt, then let me move to week 12. So in week 12, we typically discuss uh, what are the different laser amplifiers and what are the different types of laser and where they are used for different practical application and what are the different nonlinear characteristics and how the laser can be used for this nonlinear process. So let us see one by one. So the laser can be broadly applied in uh, three fields. One is metrological and scientific application, where this application requires high monochromaticity and coherence and directionality of the laser. So they exploit these properties for this application, metrological and scientific application. So next is the industrial and medical and military application. And if you by the name you can guess this require high intensity and peak power requirement of the laser. So that is why they are using laser for the military, medical and industrial application. And the third application is optical communication, information processing, and storage, which uses many properties, many characteristics of the laser for different for this application: optical communication, storage, and information processing. So we typically use light waves for communication purposes. So light waves is not it's nothing but a part of electromagnetic spectrum. So electromagnetic spectrum, I think everyone knows. So this is the typical diagram of electromagnetic spectrum. So where you have when you move from radio wave to ultraviolet, then the frequency of these waves are increasing and the wavelength is decreasing when you move from radio wave to ultraviolet. And for radio waves, the frequency is around in the order of megahertz, which is 10 to the power 6 hertz, and used for radio communication. And microwave, which is frequency around 10 to the power 9 hertz, it is used for the application like TV and telephone. We typically use microwaves for this communication. And for light waves, if you want to calculate what is the frequency, then the light waves have frequency around 10 to the power 14 hertz. And you can use it for internet application, TV, and telephone. So among these wavelengths and among these different spectral regions, so we typically use light waves for optical communication. So what is the reason behind it? So reason is the frequency. So if you see the frequency of the light wave, it is in the order of 10 to the power 14 Hz. So this means the light waves have higher carrier frequency. So higher carrier frequency means the the bandwidth of the system can be increased also. So because the communication bandwidth it is directly related to the carrier frequency and higher frequency of the light wave means it can mm, transfer a high communication bandwidth, and so that means the information carrying capacity of the system can be increased by using a light waves. So these are the different reasons of using light waves for communication purpose. And for a typical communication, there are mainly three components. One is optical transmitter and a fiber link and a optical receiver. So optical transmitter, it is typically behaves like a source. Optical fiber link, it behaves like a transmission medium where you can propagate your information. And optical receiver is the end where you convert the optical information so that you can retrieve the original signal. Okay, so for one-way communication, the optical transmitter is a transmitter only. But when you have two-way communication, then the optical transmitter can also behave like a receiver. So as I have said, the transmitter has optical sources and the receiver has optical detector. And depending on the length of the link, various optical component like amplifier and dispersion compensator can be required to retrieve the signal that is propagating through this optical fiber link. So let us see first what is the optical fiber. So optical fiber, as I've said, it behaves like a transmission medium to propagate your information. So if you recall, the main two layers of a optical fiber is one is core and another one is the cladding. And the light that we propagate, that we send through this optical fiber, it is guided by means of total internal reflection. Okay, and to give a brief introduction, so total internal reflection. So when you have a medium, so when you have an interface between two different medium N1 and N2, so when light travels from one medium to other medium, we'll see reflection and transmission. And after certain angle, so what we will see, so if you see the red lines here, so the red line, that is the angle theta c, the light will graze the interface. Okay, so this is the critical angle of the interface. Now, if you see the blue one, so for this ray, the angle is greater than theta c. So that means the ray that is grazed at theta c will be reflected back to the same medium N1. And for TIR, that is total internal reflection to happen, what is the condition required? So the refractive index of the first medium, that is the medium where the light is propagating, should be greater than the refractive index of the surrounding medium so that it can reflect it back to the same medium, and the angle, that is theta should be greater than theta c. And this condition, if you see in an optical fiber, that is N1 greater than N1 greater than N2, it is done by doping in the fiber. So if you dope a fiber, then you can satisfy this condition to get total internal reflection. And theta greater than theta c, it defines the numerical aperture of the fiber. So by numerical aperture, that means what is the maximum angle of incidence that can be guided inside the fiber. So when you have a fiber and when you launch the light at this end, this input end, so this numerical aperture defines the cone of this angle where within which if you incident the light, it will be guided inside this fiber through total internal reflection. Okay, so and so these are some basics of total internal reflection. And using optical fiber, you can use it for long distance communication, submarine and terrestrial communication, or you can use it for local access or regional purpose. So let us see how the information is being guided inside the optical fiber. So if you recall, in the laser oscillator, we have seen two types of mode. One is longitudinal mode and another one is transverse mode. And in a optical fiber, when we say the mode, we are basically focusing on the transverse field profile of the propagating mode. So, uh, so when you launch a light, only certain field pattern will survive, will propagate inside the fiber without changing, without going any deformation. Okay, so the mode here means the transverse field profile that propagate inside the optical fiber without undergoing any deformation. So we'll see the different kind of mode. So light propagation inside this optical fiber, it is determined by Maxwell's equation, and the modes of propagation it is obtained by solving the Maxwell's equation at the core cladding interface. Okay, by solving this Maxwell's equation, we'll get different type of modes, and this mode by we mean the allowed field distribution. And these figures are the typical examples of different types of modes propagating inside this optical fiber. So by mode, as I said, this field pattern when it propagate inside this core of this fiber, then it will propagate as it is. So the field pattern will not experience any kind of deformation. So only minimum deformation it may experience, but the field pattern will remain same. So the first one is in optical fiber. In optical fiber, we say it is LP01 mode. LP means linearly polarized mode. So first one is LP01, LP11. So these are I think not required for this. The details is not required. So these are the five different transverse modes of a optical fiber, and depending on the capacity of the fiber, we can divide the fiber into two types. One is single mode fiber, where only one type of mode can propagate inside this optical fiber, and another one is multi-mode fiber, where it supports different many modes to propagate inside it. Maybe LP01, LP11, they both can simultaneously propagate inside this multimode fiber, but only one type of mode can propagate inside this single mode fiber. And for long distance communication, we typically use single mode fiber. And these are the different types of method that has been used for signal transmission. One is amplitude modulation, another one is frequency modulation. So what do you do in this system? So we use the signal that we want to transmit, and we use a carrier which is high frequency, and this is the carrier is constant amplitude and constant frequency. So using amplitude modulation, what we do, we modify the carrier frequency amplitude according to the amplitude of the signal frequency. So whenever the amplitude of the signal frequency is low, the carrier amplitude frequency will become lower, and whenever it is high, it will become higher. So depending on that, you can see this is the amplitude modulated signal. And in frequency modulated, what we use? we changes the frequency of the carrier frequency depending on the amplitude of the signal. So whenever the amplitude is low, the frequency is lower, which is shown in this region. So if you see this region, the frequency is lower as compared to other region. And whenever the amplitude is higher, the frequency increases. So if you see this region, the frequency is higher than the frequency at zero. So normally it is this type of modulation has been used for signal transmission in earlier days. But now we widely use digital communication for signal transmission. So instead of modulating the amplitude and the frequency using a carrier wave, in this digital communication, the analog signal, that is the signal we want to transmit, it is sampled at a switchable rate. So we sample the signal at a periodic interval, and at each sampling we represent the information in form of bits, either 0 or 1. So if you see, and in this figure, the T1 and T2, it defines the sampling of the analog signal at time T1 and at time T2. And this is bit sequence like this, and this is bit sequence like this. So in terms of ones and zero, we represent the analog signal and we transmit it through this optical fiber. So in digital communication, we sample the analog signal and represent it by zeros and one. And this digital communication had advantages over this amplitude and frequency modulation technique. And typically, the one of the main advantages is higher signal to noise ratio. Okay. And when we talk about optical communication, that is transmitting the signal through laser, what we do, so we represent the one of this bit by a pulse which is on, and zero we represent it by a pulse which is off. So we have this coded electrical current signal from this by sampling the analog signal. So when we feed, so depending on the coded electrical current signal, what we do, we control the laser pumping. So we continuously switch on and switch off the laser diode according to the coded electrical current signal. And in the output, what we have pulsed signal which mimics the coded electrical current pulse. So here it is 1 means there is a pulse and 0 means there is no pulse. Okay. So by this mean we can convert the electrical signal to a optical pulse. And as we have seen, a digital 1 correspond to an optical pulse and digital 0 correspond to no pulse at the output. Now we'll see how this signal is transmitted along this optical fiber to a and how it is recovered at the end. So this is the signal we want to transmit. So first we'll sample the signal at a periodic interval and we represent it in terms of bits, and we feed the signal to a laser transmitter. And the laser transmitter, depending on the coded electrical signal, will see the coded optical pulse train, which is a sequence of 1 and zeros. And this coded optical pulse train, it is transmitted through a optical fiber link through total internal reflection. And at the output, we'll see a coded optical pulse train like this. And this pulse, which is at the end of the optical fiber, is fed to a receiver, and receiver, it is nothing but a photo detector, and it generates equivalent current based on the received optical pulse, and by signal processing the coded optical pulse trend, it can recover the input analog signal, which is shown in this figure. So if you see this figure, this is the recovered signal. So in this way, the electrical signal can be transmitted through this optical fiber link and can be regenerated at the output. Now, one main uh, difference that you can notice is here you can see the optical pulse train and here the optical pulse train. These are different. Sequence is okay. Sequence is equivalent. It is it is the same. Sequence is same, but you can see there is a dropping of amplitude here, and there is a spreading of pulse. And this spreading of pulse and dropping of amplitude, it is because of the optical fiber link. So the medium that is used in the optical fiber, that is doped silica fiber, they introduce losses and dispersion, that is the pulse spreading in the coded optical pulse train. Okay, so these are because of the optical fiber link. Now we'll see uh, how we can overcome these losses and dispersion that is happening in a optical fiber link. So these are some of the requirement for the source. So to minimize the loss in the optical fiber link, what you want the emission wavelength of the source should correspond to the low loss window of the optical fiber. So we'll see what is the low loss window of the optical fiber. And the second requirement is spectral line width of the source should be as small as possible, typically less than 0.1 nanometer, so that you can differentiate the pulse and there is no pulse overlapping at the output end. And the third requirement is the source should be directly modulated at a rate of gigahertz. So these are the three main requirement of the source for optical communication. So now let us see what are the first requirement. That is the emission wavelength of the source should be it should correspond to the low loss window of the optical fiber. So this is the typical loss spectrum of a silica based optical fiber. So if you recall, the optical fiber consists of two layers. One is core, where we dope the core layer so that the refractive index can be increased inside, and the cladding, it is typically of silica only. So N1, N core, it is greater than N cladding when you dope the core by, let's say, germanium. And the loss spectrum of this silica based optical fiber, it is this figure shows the loss spectrum. And there are different windows that has been proposed in different times. Like the first window, it is proposed earlier, which is frequency, which is losses around. I think this is not visible. It is losses around 2 dB per kilometer. And there comes the second window where which is around 1300 nanometer, which is losses around 0.5 dB per kilometer. And the lowest loss window, that is the third window that is used nowadays, it is losses around 0.3 dB per kilometer. And this, if you see the losses as we move from 800 nanometer to 1600 nanometer, the losses gradually decreases, and there is a peak here, and there is a loss, there is a minima here, minimum in the loss around 1550 nanometer. So, so we'll see this window now, the third window, that is the low loss window of the silica based fiber. And this gradual decrease in the losses from first window to third window, it is done by it is done by purifying the glass. Like as the time progresses, more advanced technology has been developed to purify the glasses. So by purifying the glasses, by removing the contaminants and removing the impurity, we have improved the glass material, and we have seen there is a low loss window around 1550 nanometer. And these are some basic information about the unit. So please go through it. So the alpha, that is losses, it is defined as minus 10 log P2 by P1. Uh, so the operating band, it is around 1550 nanometer. Now we have subdivided this band from 1300 to 1650 to a sub band. One is old band, which has been used earlier, extended band, and there is a S band, conventional band, long band, and extended long band. And the currently use is around 1550 nanometer, where we see a loss around 0.25 dB per kilometer. And this loss of 0.25 dB per kilometer, it is due to Rayleigh scattering. Okay. And this is the fundamental limit. We can go beyond that. So fundamental limit is imposed by Rayleigh scattering. And if you take, let's say, for which power it is, the loss is around 15%. So if you put alpha equal to, sorry, so if you want P2 by P1 is half, then it will come around 3 dB. So that means when the output power is around 3 dB, then you have 50% loss in the power, input power. And if the optical fiber link has losses around 0.25 dB per kilometer, then you can see if you multiply 0.25 to 12 kilometer, then you can see the signal. The power that you will receive at the output end will be 15%. But when you want a long distance communication, like from communication from one state to other state or one country to other country, then for that we need to overcome these losses. We need to overcome these losses. And for that, what we use different type of, let's say, dispersion compensator and EDFA, so that we can retrieve the signal in different region. Okay, so so we have discussed the first thing, that is, for the source, the wavelength of the emission should correspond to the low loss window of the optical fiber, which is around 1550 nanometer, and it has the lowest loss of around 0.25 dB per kilometer. And the second one is spectral line width of the source should be as small as possible, typically around 0.0 less than 0.1 nanometer. So let us see. So this is the typical uh, method where we transmit different signal at a time through a optical fiber. So we use WDM to transmit lambda 1, lambda 2, lambda 3 different signals at a time simultaneously through the same fiber. Okay, and to differentiate this lambda 1, lambda 2, lambda 3, lambda 4 at the output end, here what we need. So let us see around the low loss window. So around the low loss window, what we need, the wavelengths, this is the standard that has been used. So around the low loss window, we want a 100 gigahertz channel spacing. So by channel means wavelength. One wavelength is one channel. So for four wavelength means four channel. Okay. So let us see what is the delta lambda corresponding to this 100 gigahertz. So These are we have already seen. Please go through it. So for LED, it is 20 to 40 nanometer, and for fabricated laser diode, it is 2 to 3 nanometer, and for DFB laser, it is less than 0.1 nanometer. And this relation, please remember this. This is highly useful for numerical calculation. So delta nu, this is related to delta lambda by this relation, which is delta nu equal to C by lambda square negative of delta lambda. And for 100 gigahertz, we want delta lambda should be separated by 0.8 nanometer, right? So that means the channels, the different channels, it should, for 100 gigahertz transmission, it should be separated by 0.8 nanometer. And to differentiate the different channels, what we want the source, the line width of the source, this one, it should be smaller than this channel spacing so that it doesn't overlap with the channels, different channels. Okay. So that is why we want the source line width, it should be much less than the channel spacing. And for 100 gigahertz channel spacing, we want delta lambda is 0.8 nanometer. For 50 gigahertz, it is 0.04 nanometer. So for this channel spacing, what we want? We want the spectral line width should be smaller than 0.1 nanometer so that the channel should not overlap and they propagate independently inside this optical fiber. So these are some additional information about the fiber link. One is the dispersion parameter, which is given by D equal to delta tau divided by L by L into delta lambda. So delta tau, it is the temporal spreading of the pulse. L is the length of the link and delta lambda is the source line width. So you can see this spreading of the pulse. That is, earlier you have seen when you transmit this kind of pulse at the output end, it becomes like this. So there is a spreading of pulse at the output. And this is the temporal spreading delta tau. And the delta tau, it is related to delta lambda, which is the source line width. So that means the lower the source line width, lower will be the spreading of the pulse at the output. And this means that we can transfer larger bit rates without any interference inside the optical fiber link. Okay, so this parameter is one of the uh, parameter that decides the dispersion and that shows how the temporal spreading is related to the source line width. So if you use different type of sources, then the line width will be different, and according to that, the temporal spreading will be different. So now let us see the third requirement, which is the direct modulation of the sources at rates of gigahertz. And this direct modulation, it is possible. If you see the direct modulation is possible by changing the injection current, IM. So if you change the injection current, the modulation rate can be achieved with few gigabits per second. And for external modulation, what we need? We need a modulator of either electro-optic or electro-absorption so that we can get a modulation rate of tens of gigabits per second. Okay. In these three requirement, that is the emission wavelength should lie in the low loss window and the spectral line width should be small as possible, that is less than 0.1, and the direct modulation of gigahertz. These three requirements, these are satisfied this by the single frequency semiconductor laser. So if you use single frequency semiconductor laser, then it is possible to achieve this requirement, and it is possible to transmit the signal without undergoing significant loss or attenuation or dispersion. And this one of the example is distributed fiber laser, which we have already seen. Okay, so let us quickly move to the next part. So this shows, uh, so these are the block diagram of communication through wavelength division multiplexer. So when you use more wavelength like lambda volt, lambda 1 to lambda n, that is, let's say 100 or 200 or many more channels in the same optical fiber link, we say this is dense wavelength division multiplexer. And when you transmit these different channels through this optical fiber link, you will typically see loss in the system and dispersion in the system. And the loss in the system can be compensated by using the EDFA, which is erbium doped fiber amplifier. So we'll see how we can use EDFA for this. So this we have seen earlier also in the input when we have signal like this in the output. So when this input signal, when it passes through this optical fiber, then you will see a signal like this. So we will see a dropping of amplitude as well as spreading of signal. And this can be compensated. The attenuation, it is compensated by EDFA. We will see this part. And pulse dispersion, that is the increase in the temporal duration, it can be compensated by using dispersion compensating element. So this is not a part of course. So dispersion compensating element, you can use it to control the pulse dispersion. And we'll also see nonlinear effects, that is the interaction between the pulses when you use optical fiber link. And we have seen how you can remove this nonlinear effect, how you can minimize this nonlinear effect by using double clad fiber. So if you pass the pump and the signal in different layer, like signal in the core and the pump at the inner cladding, then you can easily minimize this nonlinear effect. So let us see the attenuation part. So we have a electrical signal and it is converted to a optical signal. Then it is fed to a optical fiber link. Then you will receive the output and you will see that there is a dropping of amplitude here. And it is then converted to an electrical signal through the photodetector. So let us say the input signal has 1 milliwatt power and the optical fiber is it is of length of 80 kilometer and it has losses of 0.25 dB per kilometer. So that means the total loss will be 20 dB. And if you use this relation, that is alpha equal to 10 log minus P2 by P1. So that means this alpha is the loss. So that means loss is 20 dB. So this is 10 log, let's say P1 by P2. This will become P1 by P2. So this is 2 log 10 P1 by P2. So that means P1 by P2 equal to 10 to the power 2, right? So that means P2 is P1 by 100. So when the optical fiber has losses of 20 dB, then the power at the output will become 100 times lower than the power at the input. So that is why when you have a power of 1 milliwatt here, so we'll get a power of 10 microwatt here in the output. Okay. So That is why we need optical amplifier, so that there should be enough optical power that can be detected by the receiver to retrieve the original signal. And for higher distance, long distance communication, we require this amplification so that there is signal power level at the receiver end. And this attenuation, it is overcome by using electronic regenerator or by using optical amplifier. So if you see the electronic regenerator, so between the transmission and receiver end, we place regenerator at different points. So after going through this optical fiber, so there will be a loss. You can see the loss is gradually, the power is gradually decreasing over a time when it propagates the optical fiber. And when it reaches the electronic regenerator, it will regenerate the power to the mm, original power. Then again, when it passed through the second optical fiber, the power now decrease. And when it reaches the second electronic generator, it will again, the power will increase and this will propagate again. Then using this optical fiber link, you can regenerate the power level at different intervals. Okay. But this has certain limitation, like it is limited by the speed of electronics. You can see the speed of light is 3 into 10 to the power 8 meter per second, but the speed of electron, it is not that comparable to the speed of light. So that is why the speed here, it is limited by the speed of electronics, and it can transmit at single wavelength only, and capacity upgradation, it is difficult and it is quite expensive. So that is why we shift to optical amplifier, which is EDFA. One a typical example is EDFA. And this optical amplifier, they amplify the optical signal without any conversion to the electrical signal. And the advantages is it do not need any high-speed electronics, and it is bit rate transparent. That is, you can transmit 10 gigabits per second or 100 gigabits per second at the same optical fiber. Okay, and it can simultaneously amplify many wavelength venue or many channels using WDM. And two different types of optical amplifier. One is erbium doped fiber amplifier. Another one is Raman fiber amplifier, so which is based on nonlinear optical defect. So let us quickly see what is EDFA. So this we have already seen in first few live sessions. So when you have EDFA, so you use WDM coupler to couple the signal and pump wavelength efficiently to the fiber link. And in the fiber link, the signal will be amplified when it passes through the erbium doped fiber. So you can see this is the amplified signal when you have a input signal like this. And these are the schematic of a fiber link. So we have tap coupler to monitor the power level at the input end, and we have isolator which transmit only one type of wave to propagate in forward direction. And we have WDM coupler to couple both the pump wavelength as well as the signal. And when it passes through the EDFA dope fiber, the signal will be amplified, and we can isolate the signal at the receiving end. Okay. So these are the summaries of week 12, part 1. So optical fiber communication employs near infrared radiation around 1.55 micrometer is the carrier wave. This is because it is the low loss window of the optical fiber, and the lowest loss, it is controlled by the released scattering. Okay, so please remember this small scientific terms, that is relay scattering or any TIR. So these are the concepts. Question may be asked based on this concept. Okay. And we have laser diodes and photodiodes, which are used as sources and detectors in the optical fiber communication. And single frequency laser diodes, such as distributed fiber lasers, are used for high speed optical transmitter. And the single mode fibers are used as transmission link. And EDFA are used for signal amplification in the optical domain. So this is used to tackle the losses in the optical fiber link. So let us move to the next part, which is lasers in nonlinear optics. So if we recall, by nonlinearity we mean the polarization in the system. It has a nonlinear dependence on the electric field associated with the propagating light wave. So in typically in a linear system, this is the general equation, that is D equal to epsilon E. This is the D is the displacement current, epsilon is the permittivity of the medium, and E is the incident electric field. And this you can write it as epsilon E plus P. And P is the polarization that is induced in the system because of the incident electric field. So this is P is the induced polarization in the medium. And for linear system, that is when we have small electric field, this P, it is directly proportional to the electric field. But uh, so let us see what is the quantitative relation. So for a monochromatic electromagnetic wave, you have an expression like this: E equal to E0 cos omega t minus kz. And for z equal to 0, we can have E equal to E0 cos omega t. And for linear system, what we have, P, the polarization, it is directly proportional to the first order of the electric field. That is, P is directly proportional to the E. And more quantitatively, P is given by epsilon chi into E. And the chi, it is the susceptibility of the medium, which represents the response of the medium to an applied electric field. And depending on the chi value, we have different nonlinearity in the system. So when you have a equation like this, when the system behaves in this manner, that is P equal to epsilon chi into E. So this means the medium is linear, and we can apply the linear optics to study the behavior of the system under the optical excitation. But when you have a higher electric field, the response is now becomes nonlinear. So the polarization, instead of epsilon chi E, you have epsilon chi E with some nonlinear term. One is chi2 terms, which is because of E square dependence. One is chi3 terms, which is because of E codependence. So that means you can subdivide the polarization. One is linear term and another one is the non-linear term. Okay. And chi2, it is the second order susceptibility, and chi3 is the third order susceptibility. And this shows the non-linear effects. And these are typically tensors of rank 2, 3, and 4. Chi2 means tensor of rank 2, chi3 means tensor of rank 3, and all. So let us see what is the amplitude of the electric field, so that we can see a nonlinear effect. So these are the some typical values that we have. So chi1, it is on the order of 1. Chi2, it is on the order of 10 to the minus 12 milli per volt, and meter volt. And chi3 is in the order of 10 to the minus 25. And the second and third order term, if you see the chi2, it is multiplied by a factor E square. and chi2 is in the order of 10 to the minus 12. So that means it will become significant when the electric field is in the order of, let us say, it it were 4. So when sorry 10 to the 4. So when E in the order of 10 to the 4, that means will become, so when E square, so it will be in the order of, so when you take it was 6, so this 12 and 10 to the minus 12 and 10 to the 12 will cancel with each other. And when you have 7, so it will become 10 to the 14. So that means the nonlinear effect will become significant when the electric field lies in this range. Okay. So for nonlinear effect to dominate in the system, we need electric field to fall in this regime. And how the electric field of the laser beam, it is related to the electric field. So to estimate it, we know that this is the expression for a uh, monochromatic laser beam at a point z equal to 0. And for this electric field, the magnetic field can be represented by S0 cos omega t. And if you find out the intensity is nothing but power per unit area. And if you calculate the Poynting vector using this relation, you will get that the intensity can be represented by n by 2 c mu naught E0 squared. Now we'll put the value to find out the magnitude of the electric field. Okay. So let us say we have a 10 milliwatt laser beam, that is power is given, it is 10 milliwatt, and beam of diameter 1 millimeter. So we have P by A value here. So if you put the value of mu 0, C and N. So N we have taken 1.5. What we have, E0 will come around 2.5 into 10 to the power 3 volt per meter for a 1 millimeter spot size. So that means if you focus the laser beam to 100 micrometer, the E0 will now become 2.5 into 10 to the 4. So it is in the order of 10 to the 4. And if you focus it in the range, in the region of cross section 10 micrometer, so we'll see the electric field will become 2.5 into 10 to the 5. And for 1 micrometer, for a 1 micrometer laser spot, it will become 2.5 into 10 to the 6. So you can see nonlinear effect for this focusing reason. So now let us see how we can observe this nonlinear effect. Okay. So, this is the typical electrostatic field magnitude for a hydrogen atom. So for a hydrogen atom, if you put the values of Q and R is 0.53 angstrom, then you get a electric field around 10 to the 12 per meter. And this electric field, it is comparable and it can be confined and focused using also laser beam. 1 minute. Okay. So this is the response that we have seen earlier also. This is the polarization expression for a when we have a strong electric field in the system, that is high intensity beam in the system. So for a nonlinear effect, the P behaves linearly with the incident electric field. And for a nonlinear effect, we see up to certain reason it is linear, but it behaves non-linearly after that. And depending on the power, the order of the sky, we can see different types of nonlinear effect. One is single harmonic generation, SFG, DFG, as well as for Chi3, we can see uh, this nonlinear effect, and for fourth order of this Chi4, we can see a nonlinear effect FSZ. So among this, we'll see the single harmonic generation in details. In single harmonic generation, that is SSG, when you pump a system using omega and you pass through a nonlinear crystal, what we see? We see a response around 2 omega as well as a response of omega. This is the single harmonic generation. For single frequency generation, that is SFG, so when you incident omega S and omega I, or omega 1 and omega 2, in the output end, we'll see omega, a response which is the sum of this incident frequency. That is, omega P is omega S plus omega I, or omega 3 is omega 1 plus omega 2. So this is sum frequency generation. So as the term say, it will sum the frequency at the output. And for optical parametric fluorescence, when you have a frequency of omega p, when you pass through the nonlinear crystal, then it will filter out different frequency, the omega s and omega I. So it is opposite to some frequency generation. Okay, so and this we have already seen earlier. This is the single frequency generation inside a nonlinear crystal. So it is so let me stop here. We'll discuss the remaining part of week 12 in the next session. I think there will be one live section on next Saturday. That will be the last live session. So there I will quickly go through all these concept, as well as I will solve the problems that is related to this week 12. Okay. So for now, let us stop this session. Let me ask whether you have any doubts in any part of uh, the slides. So Nitish, do you have any doubts in the slide?
Yeah, no any doubt.
Okay. So, okay, let us meet on the last live section, which will be on Saturday, same time 4 to 6. So I think the problems that I've solved will be useful to you for appearing in the exam, as well as the concept that I've discussed. It is all clear to you. Let us meet on the next Saturday. So thank you all for the joining the section.
Okay,
So
thank
let
you.
us meet on the. Okay. So bye.